Hi, and welcome to another exciting edition of 3D game programming. My name is Nate Nestler, and this is for Hyperactive Studios. Now, we left off before with some screen space shaders, but we're going to go ahead and move forward here with deferred shading. Now, last we left off with the depth shading, but we're going to take it a step further now. So, not only are we going to do the G buffer and the Z buffer, but we're going to do several passes here. And this is a advanced technique that's used for handling shaders, and it has some serious benefits to it, dealing with doing Z depth tests and stuff like this with the occlusion, so that way we can remove things that are blocking it visually or whatnot, and then you can actually in that process for the different steps inside the game engine. Now we can't do this inside the FX Composer or whatnot, or inside of RenderMonkey or anything of that nature, where we're coding out these different shaders. However, this is something we could do in the pipeline, but we can also code this process out, just so that we get the working process inside of these other programs, and we're going to do that actually. And so this is the theory video behind how it works and why do we care, more or less. And well, real quick, why do we care? It's a performance boost. We definitely get a major gain in performance. So let's just hide lights that not compute lights that aren't even going to be seen or have any effect on the scene that are there, because they can be completely occluded if they're like behind an object or something of that nature. Say they're like behind this ball exactly. You wouldn't be able to see the light from either side of this ball no matter what you do. Well, there's no point in rendering that light then, because if you can't see it, then who cares, right? Well, it's basically the idea here, so we wouldn't need to render that light, and that would save us quite a bit of computations. Same thing goes with objects. Say you get some object in front of you, like say this box is like covering up this portion of the screen here, you know, all the way up to, I don't know, like that right there. Well, let's just say it takes up this amount of space right here for the box and is blocking it. Well, we only need to render part as torus. We don't need to render these other parts here because they're being completely occluded. So for objects that are being completely occluded, you can remove them from the processing for the transforms, for move, rotate, scale, etc., from the actual engine to ever be processed in the first place, to have shaders applied, etc. So there's no need to calculate them. So this gives some certain advantages to it. The downside to it is that you end up generating quite a bit of images that go into the G buffer, and this can end up overloading the 3D card. And so that's the downside to it. Because if you're trying to do lots of different light models and shaders and stuff like that, you can overwhelm it fairly quickly, so you have to be careful about that. The other aspect you have to worry about here is that, well, I guess actually, let's step back for a second. If you have your lighting, deferred lighting, you can have deferred shading, you can do deferred lighting too. If you defer your lighting, however, you will get a boost in speed in the fact that you don't have to have all the stuff thrown into the G buffer. On the downside on that, though, is you have to render geometry twice, so that kind of hurts, because now you're doing twice the calculations for the geometry. So some benefits are gained here and some benefits are lost. But you know, it is used a lot. It also makes it easy for integrating with screen space shaders and things of that nature. And so, you know, it certainly makes things quite nice. Here's an example of it here. So if we have the color pass here, like so, this would be your Z buffer pass, or your depth pass, if you will. This right here would be your normal buffer. And then here's all these parts put together again, combined back together in another pass that goes into the final pass for what's seen on the screen. And here you also have shadows and things of that nature, which we'll get into later on. I really love this wiki. This is really well written. I'm becoming a big fan of Wikipedia for this stuff, because not only do they do, sometimes they do very good descriptions, other times they get a little too much complexity for someone who's trying just to learn it. It ends up not being such a great resource for as like just trying to get an idea of what something is from time to time, because they just dive into the depths of it really quick. But on this one in particular, it's really good, and they do go over different methods for how to handle the actual well, anti-aliasing. Because one of the things was, okay, so yeah, there's several drawbacks. Let's talk about that for a second here. One of the drawbacks to doing this is that when you're doing this method, you lose your anti-aliasing. It no longer works. That's a problem. But there are some methods to where you can go in and actually blur out those edges, doing edge detection, which we haven't gotten to yet. We'll get to it later. It's used a lot for toon drawing in particular, but we'll get into doing edge detection eventually here in the series, so that you can also do toon shading in your 3D application here and in your engine as it is. And we'll have a look at what we can do here with that. But this is one of the methods. I actually kind of like this method, but they have white papers in here for these different ones. You see these little PDFs next to them. These are the actual white papers on these techniques. That's awesome. So if you need to add this, well, you will if you do this method inside your engine. If you basically if you implement a deferred shading or deferred lighting method in here, you'll need to actually smooth out those edges. And here, this has the white papers on how to do it. And I know the MLAA one actually has some of the code that you would need in there inside of this white paper. So very cool, absolutely awesome. And this thing's got a wonderful wealth of white papers and things of that nature that you can make access to. All right. So all right, so like I was saying, you could do a course of the Z buffer or early Z buffer testing. So again, this has to deal with occlusion and, can you get around it? Now, a really good explanation of this, and I'm not allowed to show it so much, but a really good explanation of this would be covered in the white paper on from StarCraft here. And if you go to my blog at nateopengl.blogspot.com/2009_07_01_archive.html. If you go there, you can get to this link here for StarCraft, or you can Google the StarCraft 2 deferred shading, algorithms here. It's just an explanation of how they went about it, how they implemented it, and some things of that nature, and why you should be interested in deferred shading. They do a good explanation about doing the Z buffer testing, pre-testing here, in order to eliminate processes that are non-necessary. They're just not necessary to calculate. So it saves you a decent amount of computation when you get this occlusion stuff happening. So that's pretty important. That's pretty cool. And they do a nice breakdown of it. So I would totally check this out if I were you. Also, it's not real in-depth technical side. It's actually more layman's as it's written. And so it's not crazy in-depth. Also, it goes over how to incorporate some of the screen space shading techniques into the paper. There's also another one that's really nice inside of the GPU Gems 3 book from NVIDIA, and it's for the tabula rasa. I can't remember chapter, so I want to say 19, but I'm probably wrong. But you just check into your GPU Gems book if you have one. If you don't have one, you might want to check out getting the GPU Gems books. They're excellent from NVIDIA. They're just absolutely awesome. I got all 3 of them, and they're just I love them. Also, deferred lighting here. I have some good papers on it up here. And typically when you see deferred shading, you also see deferred lighting go along with it. In the case of StarCraft, they have deferred lighting to go along with their deferred shading. And that's not a surprise, really. Again, you want to be able to support all those different shaders. In order to do that, you need to have deferred lighting. Otherwise, you limit yourself on what you can have for shaders. I'll prove what I mean by that. So, for instance, you'll notice that it looks like the same shader is applied to all the geometry. Well, that's because it is. Check it out. The moment I create this sphere, it is also shaded with this. Now, I can assign whatever shader I want to it, but it doesn't really matter. It's actually applied to it right now, and it's going to override anything else that's applied to it. So that's that. But I can actually have multiple shaders applied to it. I'm not going to do that in this setup, because I'm just, as it is, it's almost 400 lines for this shader code for this part alone right here. But you can actually have multiple shaders done as deferred shading method. This is really more of an aim at just going over the actual technique itself, as get an idea of how to go about it, and not so much how to implement a full entire deferred shading system that would cover every aspect of everything you could think of type thing. We're not doing that. That is really involved, and you couldn't even do it anyways in FX Composer anyhow. You would really need to do, well, I don't think you could. I can't imagine you'd be able to do that. Pretty much you need to implement that in a actual game engine that you're coding, that you'd have full access to the code, because it's not going to be there otherwise. But as you can see, check it out, I have my different passes here. So I got my color pass, I got my normal pass, I got my view pass, and then my ZDef pass, which is not showing up as always, seems like. So this is the depth here, and it has nothing for depth, but if there was some depth there, that's where it would show up. But yeah, very cool. And you'll notice that's interactive. So yes, this is actually being computed on the fly. It's a screen space technique here. As we go, so you see as I zoom in and out, see how it changes on the images over here. And so this is what deferred shading is, basically. And as we manipulate our scene and everything, is calculating this on the fly. So all these passes can get computed later on in a second pass and be applied to the scene. So this allows us to handle lots of lights. I saw one that was talking about having 50 lights in the scene through this deferred shading. And you can dream about doing anything near that number for dynamic lights. Now, we're not talking about pre-baked lighting here. We're talking about dynamic lights. All right, 50 dynamic lights in the scene. They could do that. After 50, it really started bogging down. But at 50, they could, handle interactive rates just fine. So, that's pretty impressive. That is really pretty impressive. And the other reason why you want to consider doing this whole dynamic lighting, deferred lighting here, is because it lets you go back to DX9 for DirectX 9 type level of hardware compatibility. This means, like your older 3D cards. And so this allows for a larger customer base, which is always important, because then you can actually make this run on a lower end system. And that's really important to do that. It's very important. In the case of, yes, DirectX 10, sure, would work with just deferred shading, but that's not so great compared to DirectX 9. Now, I remind you, if you're using OpenGL, you're probably going, well, I'm using OpenGL. I'm not even using DirectX. It doesn't matter. We're just talking about what kind of hardware. Basically, when we're saying DirectX 9 or DirectX 10 here, we're saying what 3D cards here are capable of running this stuff. Are we talking about 200 series NVIDIA card, or are we talking like an 8800 NVIDIA card or something like that, or a 9600, where one of those cards can be able to run it? So if you have some of these older cards that can run it, again, more customers, make more money, and still support the graphics. So there's definitely some benefits to this, and it's certainly something I would not ignore. Now, this wiki does a really good job of doing a full breakdown of all the benefits and the problems and how to work around the problems and all this stuff. It's great. It is really good. Over here, when they're talking about the G buffer, in there, they're actually talking about these right here. So these are our render color targets here. And this is actually the Z buffer, stencil buffer, to be accurate. And so yeah, all these are getting computed. Okay. So with this said, that goes over that. Oh, also is a problem for doing transparency, by the way. Yeah. There's a way of doing some other types of methods. Depth peeling and there's several different depth methods you can have out there that can make accessing this stuff for postponing your order for your calculations for your drawing on your surfaces for transparencies. That's really covered really well in the GPU Gems books. I can't remember which book covers the depth peeling in particular, but yeah, they cover a bunch of the stuff I'm talking about in those books, and they're really good as far as that goes. So definitely check out those books. And after you're done with the shading series here, you'd have a really good understanding of how to implement this stuff hands-on, and a good understanding of the technology underneath, underlining with the setup here. So after you're done with this whole series, you should be able to read books like GPU Gems 1, 2, and 3 easily, and it won't be you know, wondering what on earth they're talking about all the time in there. It should be fairly straightforward for a lot of things after you're done with the series, because you should have a good, strong understanding of a lot of the underlying technology and everything that's happening, and a lot of experience coding it at this point in time. After a certain point here, we'll have a lot of the techniques worked out, and so that will make. There's more though. I'm not going to cover everything. You know, there's other books out there that are great for that, and I'm not trying to do an exhaustive series where we cover everything that is ever coded, you know, in shading. But the idea is to get you to the point where you could easily look at these other techniques and move forward with them. Okay, so that's cool, and that gives you a good breakdown of how this works. For some reason, the browser is no longer interacting with me, but oh well. Also realize these normals here, because this is a multi. I want to talk about something else here too, real quick, on another portion of this. See, you have this normal pass here. Well, I'm going to bring up this point now ahead of time, so that people are thinking about the right thing. Good grief, it just suddenly flipped out and went where it wanted to go. Okay, great, good times. All right, so basically, you know, we're doing this normal pass here. So check it out over here. We got these normals that are generated, right? Well, how's that happening? Well, remember this whole normal thing here? Now that's important to understand, because we're going to be computing. We're computing the normals on the fly at runtime, and then we're creating a normal pass, and then we're reading those normals back in from the image and converting them back in to an actual vector again. So we're going from vector to pixels, then from pixels to vectors again inside of this process. And you have to do that. And the reason why you have to do that is because it is multi-layered. You know, it's this multi-layered, doing these things in passes, so that way we can compute them in another pass at another point in time in the engine. This helps free you up to do things and speed things up by combining the processes to where you can handle them all at once. And so it makes things go faster. You get some deferred capabilities this way, and this also means you can avoid computing things you don't need to compute. So there's some benefits to this, some really nice benefits, in fact. Okay, so let's look at what we can do here. So something I want to point out to you real quick. And that has to do with this part here. So we're converting our normals, going from our -1 and 1 for our range here, and this would be our vectors. Normalized vectors would be within this range, right? So that way we have just a direction on them. Cool. And then that would let us convert them into pixels. All right. And so now we got our 0 to 1 pixels range here for RGB. So don't forget about this formula, you know. You have to have this working here for us to work overall. It's kind of important. Indeed. Okay. And then the other one we have is over here, where we subtract our, so in this case we divide it by 2, and then when we add 0.5 to this one, we're going from what, the actual vector itself to the pixel, and then we want to go from the pixel back to the vector, then we do subtract it from 0.5, and then we multiply it times 2, and that gives you back the actual vector fairly reasonably accurately. So that's an important aspect for handling this stage of the pass in the system. Okay. Well, with this, and don't forget, you can also apply your other techniques like your radial blur with this into this process. You can fix it in with those, and then you can also manipulate it with glow and other techniques and things of that nature into these passes, because they are computed out here, so you can compute them at another point in time where it's ideal for you. And GPU Gems has an actual white paper on it for process for how to actually, what they found to be the most advantageous pipeline method for how to go about this and everything to implement in your actual engine. So very cool, very important. Right now we're doing MRT, which is multiple render targets. So that's what MRT stands for. And that's what we have over here, multiple render targets. So we actually have 4 render targets here, but we could have a lot more than 4 if we wanted to. And that's very possible as far as things to do. But with that covers the theory aspect to deferred shading and deferred lighting. And here's just a short list of some of the games that use deferred lighting. So you'll see tons of your awesome favorite games in here, no doubt about it. And then also deferred shading in commercial games. You'll see tabula rasa and all kinds of different ones in here. StarCraft uses deferred lighting in theirs. And then here's some of the engines that use it too. And you'll find that pretty much almost all the engines use it. CryEngine, Unity, Unreal, etc. Some of these other engines too. You get a whole listing of it. And the other thing I love about this wiki is the fact that they have all these unbelievably large number of white papers and things of that nature. Lots of great references in here. Definitely something to check out. So by all means, please do check out. They have a lot of good resources for deferred shading. I'm very impressed with this wiki. It's one of the best ones I've seen yet up here, and it's really well done and does a good job breaking this down, going over the differences, and then pointing you to the actual information you need easily here for the white papers that will make this much easier to implement and make it actually work. So very well written. Also, I have some very nice white papers, tons of them actually, if you start looking at it. Some of these links have many white papers at a single link here. So feel free to check them out, as we've got a ton up here. I've got a ton of them up here. And it'll definitely make a difference for you understanding the stuff if you get some nice white papers break things down for you, and also so that you can implement techniques above and beyond this training series, because we're only trying to get you to pro level, but I'm not going to cover everything there is. So it's not like, hey, we're going to cover everything you can imagine us doing. Instead, we're just trying to go, all right, so how far can we get you up to a point where it's current gen, next gen, but then at this point you can pick up and learn other techniques that come out and other things that happen. So that's the idea here, and that's what we're aiming for. All right, well, that's deferred shading theory aspect of it, and in the next videos we'll go over actually implementing this and coding this out and making it work. All right. Well, with that, my name is Nate Nestler. This has been for Hyperactive Studios. Thank you very much. Alright, so now we're going to move on to coding this shader. So getting started here, you're not going to be able to keep practically anything you have from previous shaders for this. This is pretty much going to be almost a brand new code through all the way for the most part here. So that's unfortunate, but that is what we are going to be doing, I'm afraid. So you need to come over here to create, come down to effect, and say CGFX here, say next, say empty, and then call it something like, oh, I don't know, scene deferred shading and lighting, or something like that. That works. MRT if you want, throw that in there for multiple render targets, because there is a method for doing it without multiple render targets. And I should point that out too. So scene rendering, scene deferred shading and lighting. I was going to do a little and sign. And sign's faster. Alright, lighting. MRT. This won't fit otherwise. Alrighty. There we go. Okay, very cool. So we got our comments here at the top. Have that put in there. Your description. You can copy and paste just copy and paste one of the shaders in here just so you have something to work with. So you type a little less. Not much less though, I tell you. But let's keep you from having to type out all the comments as much. Alright. So as far as that goes, I'm going to get moving with this. Let me go ahead and zoom this too. Hold down Control and roll that mouse wheel. There we go. That's just a little bigger there. It's nice. I'll move this over here, shrink that down. I'm going to shrink this down too so you can see a little bit more of both here actually. There we go. And that works. And it gives us more code space here. So that way we can be zoomed in and seeing what's going on without having to worry about not being able to visually see the code here on the screen. Alright, I think that's big enough. Alright, so float here script : standards global. Open lesson sign here, string UI widget equals in quotes none close quotes semicolon, string script class equals in quotes scene close quotes semicolon, string script order equals in quotes standard close quotes semicolon, string here script output equals in quotes color close quotes semicolon, and then string script equals technique 0 semicolon close quotes semicolon, and then close the annotation with the greater than symbol equals 0.8 semicolon. Okay, so why are we doing all this? Well, scene here is going to make it a screen space shader. We're doing standard because we're staying in, we're not doing the pre-process or the post-process, we're doing it as we're rendering the model. So we're actually doing this compositing and the screen space technique while we're actually rendering the models, and that's why it's called deferred shading, because we're not doing it in post or pre, we're doing it at the time of the actual model processing. It's quite interesting, actually. Of course, we're going to output color because it's going to be color. It's going to go to the screen eventually. But first, it's going to go to the G buffer. Now, we'll get into that in a second. The comments here I was put in matrix forms. I couldn't remember what I put in there previously. These are different types of forms of matrices here for doing your worldview projection matrix and whatnot. So I just put that in there because I couldn't think of what I was doing earlier. I'm tired. I haven't slept much, so I'm wore out, and you'll have to forgive me. I just don't even remember what I typed, and I don't care. Alright, so with that, let's go on here to our matrix forms. Okay, so we have a float 4x4 matrix here. It's a worldview projection matrix, worldview projection here. Open the annotation here so we have it set to none so it doesn't appear in our options over here. So we don't want to deal with that. So you're going to set that up here as such. So open lesson sign here, string UI widget equals in quotes none close quotes semicolon close greater than sign semicolon. Then float 4x4 view IXF colon here view inverse. This is our view inverse matrix. This is greater than less than symbol, sorry. String UI widget equals in quotes none close quotes semicolon here greater than sign semicolon. So that sets up our view inverse here. So float 4x4 matrix for world X, or just basically our world transform matrix, basically. And then we're going to say open lesson sign here, string UI widget equals in quotes none, as you guessed, close quotes semicolon. Feel free to copy and paste. Grab one of these, copy and paste it over and over again, and then change this part up here. There you go. That will do it a lot faster than hand typing all this. Float 4x4 for worldview IXF colon worldview inverse here. Open lesson sign string UI widget equals in quotes none close quotes semicolon. Open greater than sign semicolon here. Float 4x4 world inverse transpose matrix here, or world ITXF here colon, and then of course we're going to say our world inverse transpose. Open less than sign here, string UI widget equals in quotes none close quotes semicolon close greater than symbol semicolon. Alright, and that is going to get us all our matrices here. 1, 2, 3, 4, 5 of them. Yay. Alright, so now that that is done, we're going to scroll on down. If I'm going too fast, my apologies. Feel free to pause the video when you need to here. I'm not trying to go too fast, but I'm kind of tired, and this type is bigger though, so maybe I'm not going so fast. I'm just worried that I am, because it seems like a lot at once, but then again the text is huge, so you know, maybe it's alright. I don't know. We'll find out here. Alright, so artist controls. So here's going to be the artist controls. Yep. Alrighty. So const here, I have const in front of them because it's a const. And I really should probably put const in front of those too, but I don't know if I care. Anyways, I'll get back to it if I care later. Alright, so we're going to do our falling shader. Basically, that's what all this is falling shading. But we're doing it in a deferred shading method. So we're going to calculate part of it ahead of time, and then we're going to calculate another part of it later on in the process pipeline. So this is cool because since you can break it up and process it later, you can do things with it. And that's really powerful, and it's very cool. It'll let you do some amazing things that you need to do in the process. There is a certain order in which you want to handle things, and GPU Jim's books has a really good implementation of how to do that, so check those out. By all means, they've got lots of amazing techniques in those books, and I think you really should check them out. I'm going nuts over them myself. I think they're wonderful. So anyways, const here, float 3 here, KA. It's going to be our ambient variable here, and then color. So of course this is going to be a color attribute. Open less than sign here, and then we're going to say string here, UI widget equals, in quotes, color, close quotes, semicolon. String UI name equals, I gotta stop doing this, in quotes here, ambient color, close quotes, semicolon. And then this is just being done at 0.8, 0.8, 0.8. So this is kind of cool. Check it out. So if I want to, I can come in here and I click on this and I can start changing the color around, and it's going to do it for all of them in the deferred shading method because they're all getting the same shader. But it is kind of fun just to play with this. But yeah, it actually is manipulating the models as you would imagine it would. Yeah. Anyhow, close enough for government's work. There it is. Okay. But 0.8f, comma 0.8f, comma 0.8f, close curly braces, open curly braces here for this whole vector of RGB. Same thing for KD. So const here, float 3 KD colon color, open less than sign here, string UI widget equals, in quotes here, color, close quotes, semicolon. String UI name equals, in quotes here, diffuse color, close quotes, semicolon. And then close greater than sign equals, and that's 0.8f, comma 0.8f, comma 0.8f, close curly brace, semicolon. Const float 3 ks colon color here, open less than sign, string UI widget equals, in quotes, color, close quotes, semicolon. String UI name equals, in quotes, specular color, close quotes, semicolon. Greater than sign equals, in curly brace here, 0.8f, comma 0.8f, comma 0.8f, close curly brace, semicolon. Const float spec power colon specular power, open less than sign here, string UI widget equals, in quotes here, slider, close quotes, semicolon. Float UI min equals 1.0 semicolon. Float UI max equals 128.0 semicolon. Float UI step equals 1.0 semicolon. String UI name equals, in quotes, specular power, close quotes, semicolon. Close greater than sign equals 55.0 semicolon. Alrighty. So there we go. I'll make sure I'm not going to mess this thing up. I wouldn't imagine it being a problem, but I'll try it anyways. By default, since we're clearing this out like it would be in OpenGL, so I'll see if I can explain this in a second here. Yeah, I was about to say, that should not cause a problem. It doesn't. Good. Okay, yeah, and that's going to be also a constant there for uniform. Why? Okay, because we're doing a clear color here. Basically what happens in OpenGL, we haven't gotten into this yet because we haven't done the OpenGL, but that's in another series. And I do go over this in the other series, but I'm just going to give you a heads up of what the clear color is. Basically, every time we go to render this frame, we need to clear out the previous frame, so that way the image isn't getting blurred on top of each other. You've seen this before when a game locks up or something of that nature, and you go to rotate it. Instead, you get like many copies of the same image over and over again, and it doesn't seem to be refreshing, and then you just get this big blur after a while of pixels in the screen. The reason that's happening is because it's not getting its clear color. It's basically not wiping the screen totally black before it starts drawing, you know, the other elements. In this case, we've chosen black because it's 0, 0, 0. Now, don't understand you could change this to a different color for the background here, and that's no big deal. And that's what's happening there. Same thing with the depth too. You know, you can have your Z depth buffer here, and it needs to be cleared out so that way you don't have the depth buffer information sitting in there from the last frame that was rendered. And this is done like, you know, games run at about 60 frames a second in order to make them interactive, because that's about what you need in order to have good interactive interactions happening in the scene. So in order to keep it well playable for the most part, games run at 60 frames a second, so this gets cleared out 60 times per second, once before every time a frame is rendered, both for the actual color for the frame and then also for the depth. So this is what's called a frame buffer. It goes to the frame buffer here. It's what we're clearing out. So we're clearing that out, and the frame buffer is what gets displayed to the screen. So we're actually seeing what's happening from the frame buffer. In the case of these G buffers, they get computed in and then added to the frame buffer. And that's what happens with that. But anyhow, going further. Alright, so that's our clear color here. Of course, it's just 0, 0, 0 for black like that. And then const here, float, clear depth here, open lesson sign, string UI widget equals, in quotes, none, close quotes, semicolon, close greater than sign equals 1.0, semicolon. And of course, it's going to clear out our depth. Awesome. Let's move on to lights. Lights, we got something different here. It's a directional light. Oh, okay, so how do we do that? Well, we do a create up here, and we go to directional light, and after we create it, we're just going to move it into position. This is my directional light right here. I want to have it where it's pointing to these elements here. Now, this is like the sun, more or less. Basically, it acts like it shoots light at about a 180-degree angle from the light and just shoots it like a whole plane of light that just moves forward into infinity and beyond. And that's what directional light does, kind of like the sun does. You know, we're considering where the point of the sun is an infinitesimal point in the distance here, so it almost comes up as a single point in space, if you will. And the light that shines from that sun is so encompassing that it completely covers, you know, well, half the Earth when it hits it. So if you're within that range of that half the Earth for that light, then essentially it's like a perfect sheet of light that's going to hit you from that same direction all across the whole portion. Think of it as like it'd be as, I mean, the sun is so ginormous compared to Earth that it's basically like, say you're in a room and the one wall is completely just nothing but light. You're going to get hit on one side by light on every portion of your body on that one side. That is exactly what is happening here with this directional light. It's going to hit you on every bit of that side of the light. Now, mind you, as you move to the back, it's not hitting you there, but anything on the front and going all the way up through in front, going on this portion of the sides here, like it would be on an actual real object or a person coming from the sun, you're going to get that same kind of solution. In this case, this ambient here, I can turn this down if I wanted to. And then we can see more of a result of light and shadow happening from that directional light. So that helps make things out. In the case of this plane, it's not getting so much of that light because it's at a glancing angle to it. It's exactly like, the light shooting at it straight on, and look at the plane is like flat compared to it. So it's not really picking up any of that light, whereas this stuff here is perfectly lined up with it, and so it's catching that light. Hopefully that makes more sense. I'm going to show it that way. And that's kind of what's happening there. So that's what a directional light is, more or less, and that's what happens when you use it. So we're going to work with the directional light in this case. So we're going to do a const here, float 3 here, lamp 0 dir here, colon direction here, open less than sign, string object, string space object equals, in quotes, directional light 0 close quotes, semicolon, string UI name equals, in quotes, lamp 0 direction, close quotes, semicolon here, string space equals, in quotes, world, close quotes, semicolon, because we're going to do world space coordinates here. And this makes sense. It makes a whole lot of sense, actually. Let's go over this real quick. We want everything to be in world space coordinates. The reason why is because this is a deferred shading. We're going to be working with many things at once, and we're going to want everything to be in world space coordinates because that makes it easy to handle everything all together. So now you don't have the issues and the headaches that you would have if they're in, like, say you had everything in its own object space. That means each one has its own coordinate system. That's not going to be too easy to translate between this coordinate system and that coordinate system. Oh, forget it, man. So you just make it all in world space coordinates, and then, that's the same coordinates as this coordinates with that coordinates, and everything works together. So by making it in world space coordinates, you don't have to worry about any issues or headaches. Just make it world space coordinates, and everybody's using the same coordinate system at that point in time, so everything just translates with each other. You don't have to do any bunch of conversion going back and forth between different objects and how you relate one to another or anything like that. Instead, you're all relating everything to the world space 000 position point, and everything's based off of that. So guess what? Everything just works off of that. Everything's compatible with everything, and you don't have to do any translation. This is that, and that is this, and that's all there is to it. You don't have to go in and do a bunch of special mathematics in order to say, hey, this is where I am relative to where this one is, which is relative to that one, which is off. Forget it. You're just saying, oh, I'm relative to 0 in the world, and that's where I'm at. And it's like, oh, I'm relative to 0 in the world here, and I'm relative to 0 in the world here. So now I know where I am, and he knows where he is, and she knows where she is over here, so on and so forth, and everybody knows where they're at. And it just makes life so much easier when you're coding this stuff. So that's why we're keeping everything in world coordinates, so that we don't have this massive headache migraine for creating this setup here. Okay, so this is going to give us our string object here, and equal to our directional light here, 0, close colon, close quotes here, semicolon. That's going to be this directional light I put in here. And we're calling it a lamp 0 direction. It's just the name we gave it. So it's going to appear over here. And of course, we went in world space coordinates, and its position starting out here, I don't know, it's told to be 0.7f, negative 0.7f, negative 0.7f, and that's fine. Close curly braces and semicolon. Const float 3 here, lamp 0 color here, colon specular. Open less than sign here, string UI name equals lamp 0 in color for the color here. String object equals, in quotes, directional light 0, close quotes, semicolon. String UI widget equals, in quotes here, color, close quotes, semicolon. And then close greater than sign equals, in curly braces, 1.0f, 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 close curly braces, semicolon. And this is going to set up our light to be white specular, hot bright specular. And that's what we want. So that sets up our directional light as it is here, and then we'll worry about it some more later on down in our calculations. But this is going to be a directional light, and we are going to, it is a little different light, and we're going to play with the spotlight later on in some shading series coming up here very soon for shadows and things of that nature that use this deferred shading as part of their techniques. So it's really important that you understand this, otherwise you'll be lost in the next upcoming videos here when we start getting into techniques that use this deferred shading for manipulating the scene to give us what we want. So makes things, this is a very important series video here, and you definitely need to try to understand this as much as you can, because it will make a big difference.